the talk I would like to give here is some views on what to do with spectrum for wireless access. Do we actually need more spectrum, or is it a deficiency of how we run things that requires a lot of spectrum? So this is some spectrum efficiency on a very, very high level. First, I'd like to draw your attention to some lessons from history here, and this is something that you may remember from economics in the 70s. It was a concept called dominant designs, and you've seen dominant designs over history that we have seen two equivalent technologies suddenly merging into one. You have this VHS Betamax example, for instance, that there were two competing standards and suddenly one won, and the other one completely disappeared. And in IT, we've seen a lot of dominant designs. We have seen Windows, we've seen Wi-Fi, we've seen LTE, and then there are some roadkills on the way, like VAP and DVB-H, and if we look at how this has all come together now, and how do we provide services in the mobile community, or I would say in any IT community, it's basically we do it like this. We have a cloud-based computation and storage paradigm. And this is simply because IP connectivity has become very cheap. So it's why do processing locally when you can do it centrally? If communication is virtually for free, if there's a zero marginal cost of transmitting something, it's better to do the computation and storage where it's as cheap and energy efficient as possible. So this is what we do, and this, of course, if you look at the infrastructures for this, if we look 10 years back, we still discussed killer apps. There was this killer application that would actually pay for the whole infrastructure. And I would call them one-trick ponies. I mean, you build a network like DVB-H to do only TV, or you do a DVB network only doing TV. And I mean, nowadays we can laugh a little bit about this, but this is how people thought. And in fact, this is actually how spectrum is managed. This is the scary part. We're still thinking one-trick ponies here. We build a vertical system from services down to the physical layer. But of course, what we see now in fixed and in mobile, we go to a more general access infrastructure. We don't think about a certain application. We say, if we provide IP, then they will come, or then the services will come. And this is really what happened. We provide general platforms rather than specific technical solutions for specific services. And of course, this means that now internet access has become sort of the dominant design for all types of services, mobile and fixed. And it tends to marginalize other types of solutions. The one-trick ponies sort of more and more disappear. And we can see a lot of stuff like wireless peer-to-peer. I think this is a good example. If I want to send a picture to Misha from my smartphone, I don't establish a Bluetooth connection. This is too complicated. I send them an email with the picture. So I do a cloud solution to do that, because I can send him a picture when he's in New Zealand as well. So I don't have to, and I use exactly the same software for that. So the scalability issue here is enormous. You think the story sounds familiar? I mean, if in the wireless world, of course, this is exactly what happened in the fixed world. Nobody discusses about building wired networks for specific purposes anymore. I mean, you provide IP, and that's it. And of course, this causes the data avalanche. We discussed this, and we can debate how to extrapolate this, but I agree with Chilin that 1,000 times is a good figure, and then we can discuss whether it's happening 2020, 2018, or 2022. I mean, I think that we're heading that way. And the exponential growth that we've seen so far is that it becomes from the fact that we sort of assume a zero marginal cost of providing additional bits we pay a monthly fee, and if we have as much as you can eat type of services, then you get this. And the question is, of course, we're going to discuss today, how long can that be sustained? And we already see some shrinking here. The key problem for the operators is if we keep doing like this, then providing more capacity requires more base stations, and if you have a certain cost per base station, then unfortunately if you want 1,000 times more capacity, you need 1,000 times more base stations, and it will be 1,000 times more expensive, and it will consume 1,000 times more energy if you don't do anything. So we're heading the wrong way here. So the question is, how difficult can it be to do this, and is throwing more spectrum as this problem, is that a solution? So I mean, you're all aware that there are three ways of increasing capacity in a system, in a wireless system. You can, if this is the total data rate, you can increase the spectral efficiency, number of bits per second per hertz, or the reuse efficiency. It's also one way of seeing is how many bits per hertz per square kilometer that you can get. And we are close to the theoretical limits. I think we can tweak a few things, and tweak a few things means maybe 5-10 times. So that's compared to the thousands, it's a very small part still. We can add more base station. That is the classical brute force solution, and in fact this is what we have been using over the years, mostly. Expensive, maybe, and then the question, can we do more spectrum? That is also, you can see if we add 10 times more spectrum, we can get 10 times more capacity. That's sort of a no-brainer. And the FCC did this calculation a couple of years ago with some reasonable extrapolation of current deployment strategies and reasonable increase in capacity in spectral efficiency developments, and they find this spectrum deficit. If we go along this path, the spectrum will run out. So obviously spectrum is not the solution, because we run out of it. So we need to do something. What can we do? Well, the solution sounds a little bit like a no-brainer, and most people have been realizing this, that we cannot deploy everywhere. We need to deploy where the people actually are. It's sort of this blanket coverage providing gigabits per second all over the country is not really the good idea. So if the traffic is shaped like this, we should do het nets, which is provides high capacity where there are lots of traffic and lower capacity where there's less traffic, and we focus on coverage in these areas, we focus on capacity in these areas. So what are the consequences now if 80-90% of the population are in this part? And this is the short range indoor. We talk about tens of hundreds of meters from base stations. If that is the most of the capacity need, maybe things are not so bad. This is my favorite picture on how to solve all wireless problems. And I think if you think about this picture, this actually summarizes everything what we need to know about het nets. This is how we do lighting, wide area lighting today. We put up big floodlights. Actually, this is a massive MIMO, isn't it? Lots of antennas. And it illuminates a stadium where there's lots of people in wide areas. Do we use floodlights to light the interior of buildings? Of course not. And why? Well, there's a 30 to 40 dB loss in the walls and in the windows. So it's extremely efficient maybe for a wide area, but extremely inefficient for indoor. So how do we do indoor? Like this. Small lamps everywhere. Hundreds of lamps inside the building. I mean, how many lamps are in this room? There are lots of lamps here. So this is how you do indoor lighting. Several orders of magnitude more efficient from a energy perspective. And I would claim several orders of magnitudes more efficient when it comes to capacity. I mean, not 10 times, 100 times, 10,000 times maybe more efficient when it comes to indoor. But what is the problem then? Well, the problem is that if we, as we see, it's not only the technology, it's actually the business, the way how we do business. The way we do outdoor floodlighting and the way we do indoor illumination is completely different. The way we do outdoor wide area mobile data services is completely different as we do indoor. We can see here in the left-hand domain there is industry grade equipment, big antennas, very high reliability, and very expensive stuff that you put out there. On the right-hand side, it's consumer grade equipment, massively deployed. SON has to be, because you can't afford to have radio engineers to deploy this stuff. And you get reliability to redundancy. You have many of these. If one breaks, no problem. The janitor can replace it next week. These guys on the left-hand side are limited. Sorry, these guys, this is cell size, and this is the relative cost of different stuff here. On the right-hand side, big cells, you're dominated by radio-related equipment, the towers, antennas, transmitters and stuff like, very expensive. The backhaul becomes a minor part. In the indoor case, the radio equipment is almost for free. What is really expensive is doing all the wiring inside. But the interesting thing with the wiring inside, it's for free for the operator or for the one that wants to install stuff inside, because it's already there. If you can use the stuff that is there, if you can use best effort IP connections, then it's for free. If you want to install CRAN, you need to put down your own wiring, and then it becomes really expensive to do it indoor. So the cost factors are really interesting here. And the problem now is this creates a dividing line, because this is done, who owns the stuff here? Who owns the majority of the investment? It's the facilities owner, the guy that owns the building. He's put down all the wiring. He owns all the stuff, and now he wants to you add a few boxes of $50 each that are the wireless stuff, which is completely neglectable compared to the cost of the rest. Of course, he wants to own the network. Here, the backhaul and everything, the massive investment is done by the operator. So there's the operator domain. Here is something else, indoor provider, and his cost benefit comes from that he wants to deploy this anyway, and he has the energy available anyway. So this is an interesting situation that affects the spectrum here. And let me just when it comes to spectrum for this, there are basically two problems that we can face. We can discuss the spectrum, long-term spectrum availability. If we would have 50 years or 30 years, and we can rearrange everything, would there be spectrum for all this? On the decades perspective, and I think on the decades perspective, it's there's not a big problem. There's we already have now 1 gigahertz of spectrum available for mobile and short range type of services, and this is plenty if we do it the right way. If we do indoor solutions, we can get massive amounts of capacity. If we try to build floodlights outside, needing lots of spectrum, we can't. There's no way. But if we can do it the right way, there's plenty of spectrum. The other problem is then, okay, this is, if I can wait 20 years, this is okay. But what do we do in the short-term perspective? Can I get access to the spectrum now? Because there are lots of other users that already use the spectrum, and that is a more tricky question. But you can ask yourself, when is spectrum availability actually the barrier? And we can't really see very many cases where it's actually a fundamental barrier. If you look at what the regulator thinks here, or what the regulator should think, these are some some directives that you could give a national regulator. How should you allocate spectrum? Well, he should make efficient use of spectrum resources. There should be some public service here, affordable communications to the citizens. There should be necessarily societal functions like blue lights and police and stuff like that should have communications, and it should promote maybe local industry. That could be typical. And it could be a longer list depending on what country you're in. But what you can see from the first part and from the first lesson learned in history here is that when you, as a regulator, how should you allocate spectrum? Well, you should allocate spectrum and give preference for multi-purpose, service-neutral infrastructure. I mean, systems for which you can do many things with, compared to one-trick ponies. So, to take an example here, and if you look at TV broadcasting, for instance, it's a one-trick pony. Mobile IP access is a multi-purpose infrastructure, can be used for many services. And from the regulatory perspective, it's obvious who should get preference, right? And another thing is important to understand is that competition, which is something usually one way to achieve affordable communication services, is not necessarily done to parallel file layers. You can get competition by allocating the same type of spectrum to several actors that then start competing. But let's say in the indoor environment, that is not really necessary, because it's really not really interesting to have 3 operators to run in this room, for instance. It's much better to have one that provides the access infrastructure, and then you can have competition on let's say the IP layer or higher layers. So it's not really necessary. Yeah. So summarizing here, if we now take our lessons learned here, how should you do licensing in the future, or on the long-term perspective? Well, you have these wide area systems, and those won't go away. They will need increased capacity in the future as well. So you need spectrum for this type of systems. And here you have you want low spectrum because you want wide coverage. You need interference protection over wide areas. So it's very difficult to confine, say that you can only use this spectrum in this very limited local area. You have to get protected over wide areas. And you do heavy investment in infrastructure, lots of towers and antennas and stuff like that. So the only reasonable solution for this is long-term national block licenses as we do today. And the advantage for the regulator is that there are few regulatory decisions, but the drawback is you create some kind of oligopolistic structure. I mean, you're stuck with these guys that have done the investment. When you go to the capacity end, local indoor system, you actually don't want low spectrum. You want high spectrum because you don't want so much interference. The interference protection is needed only over very small areas. In fact, if it's basically you can have one base station every room and get very effective interference management like that. And the investments in radio is really small. So and the bulk of the infrastructure, as I mentioned, is owned by the premises owners. And of course, having national block licensing for this makes no sense. Why should I prevent somebody else from using the same spectrum in the next building if I don't interfere with him? So here we need different licensing methods, like could be unlicensed, could be light licensing, or really local. I can get a license for this building, for instance. That type of solutions we need to see. And I think that is a really challenge. And how do we what kind of license regime do we need that gives the necessary protection but doesn't give the operators too much market leverage? That is unnecessary market leverage by giving them national block licenses. Yeah. Okay, some conclusions here. Wireless cloud access, I think, is the dominant design for future services, or at least in the next couple of years, and tends to obliterate other services in volume. There will be, of course, other ways of solving things, but this will be the big mass market and the big demand for spectrum in the next 10 years. And a problem that we see is that as we go for more and more high capacity, that will tend to dominate the marketplace. But the rural guys tend to have a problem because they're still not very profitable. There are few users and large areas. So if I see there are two areas where infrastructure sharing can be really interesting. So is it indoors, and it can be in rural areas. And there's room for competition in the middle, where there's sort of suburban areas and city centers outdoors. I think there's an interesting room for competition. And as we can see here, spectrum is not really a fundamental limiting factor. If we want to solve the problems as we do today, with fewer base stations, of course, we can spend a lot of spectrum to solve the problem. But it's not really interesting. It's interesting to see if regulators will actually take this standpoint. When should the regulators say that, okay, guys, you can't get more spectrum. You have to solve this to indoor solutions, and you can get 4 to 6 gigahertz. There you can operate, rather than handing out more and more spectrum and to sustain a business model that is not really sustainable in the long term when it comes to energy and cost. Okay, so I think I'll conclude there. And if there are any questions, or are you completely in shock still, or? Okay. Misha, one question.
Thanks. So, okay, it seems like, you know, probably all have seen the press release of Samsung on 5G. So it seems like they just simply got around this problem by moving above the 10 gig band, where there's a lot of spectrum available, which so far has been a real barrier because the electronics is very expensive. But if we look at an iPhone, which costs, you know, 300 euros to produce, and they sell at 500 euros, probably this electronics plays just such a marginal role that there doesn't seem to be a problem anymore of just going in higher frequencies. So maybe we couldn't just skip all the discussion about the lack of spectrum and just move up in the band, maybe below 20 gig, but above 10 gig where there's a lot of spectrum available.
Okay, yeah, I agree. If you go to high frequencies, you get less of a problem with interference. That's the good thing. But the problem is then you get serious coverage problems. And for instance, if I put my phone in the pocket like this, I'm out of communication. That is the bad thing with if you go above 10 gig. So there's a trade-off to be struck. I mean, if you go above 5-6 gig, then body shadowing becomes in furniture and everything becomes a significant problem. So we're not talking about mobile communication as we're used to it anymore. We have to worry about how to place things and should I put things in the pocket and things like that.
More comment on that, I guess even if you go up to a higher frequency, I mean, it's not like 1,000 times more spectrum up at the those bands, I guess. Then we talk about your like factor of 10, which probably solve, but we still, of course, need to go to a lot of densification.
Yeah, I had a slide here on not all spectrum bands are equal. I mean, there are lots of if you introduce different frequency bands, there are different constraints that apply, and this is unsuitable propagation conditions is only one thing, but there are other types of issues that can counter sort of outweigh the benefits of getting more spectrum. Last question from Gillian.
Yes, very interesting talk, Jens. It's interesting now that I think I'm finding the sixth pearl, because in the 5 pearls that we shared, there are a couple things that we kind of point out that this is a time to think differently from the previous generations, right? Before it was just spectral efficiency. For 5G, we should look at SE and EE together, a co-design. Before, it's like the traditional cellular concept has been in mind when we started each of the new generation of standard design. But now we really started thinking of the network not being homogeneous, that no longer traditional cell-based design. But now from your talk, it seems it actually touched upon an issue that has been, I don't want to say troubling, but has been in existence since the late 90s, which is, for example, what do we do with Wi-Fi? Right? In the late 90s, 3GPP had, I remember, designed 6 different levels of degree of, from the tightest to the loose coupling of the Wi-Fi with the cellular network. But none of that had really materialized, even though the 3GPP had laid out the 6 different ways. But now, when we look at the global environment, Wi-Fi is a non-deniable important existence. Even, for example, in China Mobile's case, we are working on what we call full network coordination, which is the 2G, the 3G, and upcoming 4G. Plus, we have deployed in the past 2 years 4 million Wi-Fi hotspots in China. It's a huge system as well. How we make all of them work together as one system, it's still a continuous challenge in terms of traffic planning, in terms of interference management, in terms of energy saving, how we make it work as one rather than 4 different systems. But I think with your proposal, we can think of 5G as an even more complex, multidimensional scenario, which is you have premises owners now coming into the picture. You'll have operators potentially, like you said, focusing on building maybe competing infrastructure in the urban and suburban area, primarily outdoor, whereas leaving the indoor to the hands of willing and capable premises owner, and so on. So I think that that part, in some sense, partially in the past 2 decades, has been kind of covered by Wi-Fi. Whether that's enough or not, it's to be debated. But the relationship, the business model, I think it's a challenging issue. And I don't know how people who are working on the 5G solution, in addition to the technical content, will be able to work on the business arrangement, because it's no longer one system. It will be kind of a hybrid, integrated system. I think it's a pearl, but it needs a lot of polishing.
Yeah. Maybe we should, William, we can maybe push this to the lunch discussion. I think that this is a very interesting topic. And is Wi-Fi enough? We see in our research, we see situations where Wi-Fi is not enough. I mean, Wi-Fi it's very nice. It's very sonish. But it has capacity barriers that are very steep. So I think that there needs to be other technical solutions for this type of scenario.